All right, since Teams is still not correctly recording when I share my screen, I'm gonna try recording with OBS today. We'll see if that works. All right. So okay, actually, before I jump to this, so I put up on the website the advice from former students that I've gotten from, like people filling out evaluations at the end of the year. You can look. I'm not going to read them all to you, but you'll notice some themes if you look through them. So I'll let you look at those. Prompt set 1 is due Friday. And also just pointing out, maybe you figured this out, but like on the days that we do a Poggle activity, there's this little Poggle icon after it. And if you click on that, it'll open up the PDF of the activity. So if you missed class or if you just lost yours and you want to, look at the activity, I mean, they're not filled in, but also in case you care, you can actually look into the future and see like which days we're going to be doing a Poggle activity and which days we're going to be doing a lecture. That may change slightly, but I mean it's probably pretty good predictor because I've run this class a bunch of times. I've got the schedule down pretty well. But I might add an extra activity or something, but for the most part. All right, so today is in fact a lecture day. So we used and we'll often do that where when we introduce some new unit or topic or something, we'll start with an activity to help you kind of build some intuition, learn the definitions, and then and then a combination of lectures and activities after that to fill out the rest of it. So that is way too big. All right, so we're going to be talking about asymptotic analysis, which is like big O, etc., all that stuff. So what I want to start with, before we even get to definitions and stuff, like why bother? Why analyze things mathematically? As opposed to like, okay, look, you want to know which of these algorithms is faster? Just run them both and use a stopwatch. Like, that would be easier in some ways, right? So why bother analyzing and I am going to say runtime specifically. Right. Again, big O is not about time. It's a more general. It's just about measuring things. But we typically are using it for measuring time. So why bother analyzing runtime, analytically at all? Right. Like why not just use a stopwatch? Any ideas? What did you think? I have a few reasons in mind, but maybe you can think of others. Henry?
For example, if maybe it's like for a big research project and it's going to take a long time. So you want to analyze your algorithm beforehand. So, because if you take the test, maybe one of them takes like 10 years or something.
Yeah, right.
You don't want
exactly.
to take the whole time to
Indeed.
know which one's going to be faster.
Yeah, absolutely. So, I mean, yeah, maybe it's literally, in many cases, it may literally be faster. Either because maybe you could run the things and time them, but it would just take a long time. Or maybe, right, you analyze something and you're like, turns out I can predict that this will take somewhere between 1 and 5 years to run. So I'm not going to run that. Let's go back to the drawing board. Yeah. Or, I mean, we're going to see examples. It's actually 1 to 3 years is not bad. Usually it's like either it's going to run in 5 minutes or it's going to run in 5 billion years or something like that. And it's like, oh, yeah, nope, not gonna happen. What else? What other reasons why we might analyze things mathematically? Jay?
Saying something is big O of n, communicates a lot more than saying it runs in this specific time on this specific computer.
Right. So it's kind of, it's more general, you're saying. It communicates more. So, yeah, so more general. And it's like, not specific to one computer or, some hardware or whatever. Not specific, to programming language, hardware, etc. Indeed. What else? Any other reasons you can think of, Nico?
Computers are finicky. Just because it's faster when you do it that one time doesn't mean it's always going to be faster.
Yeah, okay. That's, yeah, good. Computers are finicky. And however finicky you may think math is, I promise it's less finicky than computers. Like you won't, if you do the same thing twice, you won't get a different answer. Well, you might, but that's because you made a mistake, not because there's something wrong with math, right? You run something on a computer and it's like, well, every Tuesday when there's a full moon, it like takes longer, and you're like, why? It's like, well, it turns out that I don't know. I agree. Good. Any other reasons? Cool. And these are the main ones I had in mind. I guess also like maybe this kind of goes with the second point that Jay was making. If you run an algorithm, like you have to run it on a specific input and time it, right? But if you can analyze it mathematically, you're sort of analyzing it for all possible inputs at once, right? And so you can say something, again, it's more, you're saying something more general, not specific. Like maybe I should just add that to the list of things that we don't want to be too specific about. Okay, cool. So that's why we're doing this. And then we'll talk more about, okay, given that we want to analyze things mathematically, why is Big O kind of the right tool for the job? And we'll talk about that more today as we go through the definition. All right. So as you saw in the activity, right, Big O is, is kind of like less than or equal to. Big omega is kind of like greater than or equal to, and big theta which, by the way, so this is a capital Greek theta. You write it by making an O, and then inside there's like a little line that goes across, and if you want to be super fancy, you put like little bars on the ends of the lines, right? So that's how you draw it. But this is kind of like, like equal to. Okay, however, that's not the definition. So, so if I have some function t of n, and I say, oh, it's O of n squared if t of n is less than or equal to n squared. I'm leaving some room here because this is not the definition, and there's some thing, like what I've written would be too specific, and we would not want to use this definition. So as written, it literally, like if t of n is always less than n squared, right? So thinking back to what we did on the activity yesterday, what might be some reasons that we wouldn't like this definition, that this would be kind of too specific for us? Nico?
Because when we have that k value, would it not be greater than n squared, even though it should still be O of n squared?
Yeah, so you're talking about like the k value, like, oh, what if we run it on a computer that's half as fast or twice as fast or something? What if something takes 2n squared, right? According to this literal definition, that would not be O of n squared because 2n squared is not less than n squared, right? But we kind of, our intuition was we don't really want to care about, like going back to Jay's point, like why we're doing this analysis, we don't want to care about like which specific computer we're running on or whatever. And so we don't really want to care about constant factors like that, right? So that's why we add, whoops, I'll make this blue. This is, I'm going to write out a more formal definition in a minute. This is still just kind of intuition, but this is the idea. So first of all, we say, well, some constant time, that's supposed to be a times. Oh, my pen is not, there we go. As long as t of n is less than or equal to some constant times n squared, right? That's fine. It could be 5n squared. That's okay, right? There's one other thing that needs to go like in here. And that is that we kind of don't really care what happens with small values of n, right? Because with small values of n, like, who knows, there's all sorts of reasons that something could be, you know, that something might not fit this for small values of n. Also for small values of n, typically we don't care because it's like, well, again, if n is 5, I can just do it by hand. I don't need an algorithm, so I don't really care how long my algorithm takes on 5 things. It's going to be instant anyway. So we kind of intuitively, we say, well, it doesn't have to always be less than that, just as long as it's eventually, right? For big enough n. And so I'm going to add this word eventually. All right. Okay? Does that make sense? All right, so given that intuition, let me give you the actual formal definition of big O. So definition. If there exists let's say an integer n0, or maybe I'll just say a positive integer, whatever, yeah, either way. So there's some integer n0 and a real number c greater than 0 such that for all n greater than or equal to n0, t of n is less than or equal to c times g of n, then we say t of n is big O of g of n. Okay, so let's think through this. So instead of talking specifically about n squared, now I'm just talking about some arbitrary function g of n, right? But g of n could be n squared or could be anything, right? So first we have this constant c, right? So t of n has to be less than or equal to constant times g of n. And then the eventually part, right? That's the n0 business. So it's like, well, it doesn't have to be true for all n. There just has to be some point that we're going to call n0, such that from that point onward it's always true. But we don't really care what happens below n0, right? And that's the definition of what it means for something to be big O of g of n, right? So I can let's draw some graphs, right? And maybe I should have drawn some graphs earlier. That's okay. We'll call this like maybe this is g of n. Maybe this is like 3 times g of n. Right, and maybe t does something like this, like it kind of, I don't know. Here's t of n. Right, so maybe this here, this is the n0, right? So it's above 3 g of n at first, but there's some point where after that point it's always less than or equal to, and you just have to assume that from here on out, you know, forever, t of n is less than that upper green line. So in this case, we would say t of n is big O of whatever that function g of n is. Okay? So, again, based on what you learned in the activity, what do you think needs to change about this definition to turn it into the definition of big omega? What would stay the same? What would have to be different? What do you think?
Flip the comparator on T of n less than or equal to C of n.
So this one here?
Mm-hmm.
Yes. That's the only thing that has to change. So if that is a greater than or equal to instead of less than or equal to, then that's the definition of big omega of g of n. So I'm not going to write the whole thing out because it would literally be the same except greater than or equal to instead of less than or equal to. Okay? And then definition, if t of n is big O of g of n and big omega of g of n, then t of n is, and we saw this in the activity, right? This is what big theta of g of n means. Right, so to draw, well, okay. So here's a question for you. It's a little bit tricky, but see, if you can figure this out. You might think, oh, to get the definition of big theta, we just change this, instead of less than or equal to, greater than or equal to, we just have equal to. That would not be the same thing as the way it's defined here. The reason is, if I just said definition, if there's n0 and c such that t of n is equal to c g of n, that's way too strict. That means like t of n eventually has to be exactly equal to some constant times g of n. But the actual definition says it has to be O of n and big omega, or O of g of n and big omega of g of n. The constants in those two things could be different. So as long as it's like sandwiched between, like let's say it's always greater than 3 g of n and less than 4 g of n, right? That's big theta, which we need because like that's a pretty typical thing. Like if you have, right, let's say this is, here's 3 g of n and here's, 4 g of n. Right, and maybe theta could do, this t of n could be like this. That would still be theta of g of n. And, I mean, okay, typically functions don't wiggle like that, the functions that we kind of look at. But even something like this, here's 3 g of n. Oh, no, it was supposed to be 4. Here's 3 g of n. Right, often, like, t does something like this, where it, like, kind of it's never like exactly equal to some constant. It's kind of asymptotically getting closer to 4 g of n or something, but it never quite gets there. But it's always in between like 3 and 4, and so that's big theta. I mean, we'll see. I mean, we've seen examples of that. Like if you just say, n squared minus n. N squared minus n is not equal to any constant times n squared. It's n squared minus n, right? But it is in between, like, probably always greater than half n squared and less than 1 n squared, for big enough n. Okay. So I guess the big question at this point is, like, why do we need all these things? In data structures, you just talked about big O, and it turns out that out in the real world, when people are talking about programming and stuff like that, like everyone just talks about big O. And usually, quite often, people say big O when what they really mean is big theta. Right? So, if you're like, oh, I just figured out why like those database calls were so slow, because we were accidentally doing like our algorithm was accidentally big O of n squared. Right? What you really mean is big theta n squared. You mean like it is actually asymptotically the same as n squared. It would not make any sense if like, well, actually it was, you know, it was linear, but you said big O n squared, because technically linear is big O of n squared because it's less than it. But that wouldn't make any sense. Like if you say big O of n squared in that context, you mean exactly n squared. However, we're going to be careful about it in this class because it gives us a vocabulary to talk about things that would be kind of hard to talk about otherwise. And we can be precise about whether we really mean that something is an upper bound or a lower bound or, you know, exact. Because there will be some situations where we really have to say big O because we don't actually know exactly what it is, but we can give some kind of upper bound, right? Or vice versa. One nice example I like to talk about, and we'll see lots of examples, but one fun example is matrix multiplication. So if you have two n by n matrices and you want to multiply them, right? And maybe you do or don't know what that means. It doesn't really matter. But if you don't know what that is, just take my word that there's things called n by n matrices and we want to multiply them. But we can, but probably most of you have seen some kind of matrices. So we can clearly say the time it takes to multiply two n by n matrices is big omega of n squared. Why is that? Well, the output is going to be an n by n matrix, which has n squared many numbers in it. And so even if the algorithm does nothing other than just write out the numbers at the output, it has to take n squared time, right? So that's a pretty clear lower bound. There's also an easy upper bound because there's an obvious, if you just, the way you learn about matrix multiplication, you're like, well, you loop over all the rows in here and you loop over all the columns in here, and then for each pair of row and column, you loop through the entries and you multiply them and you add them all up, right? So it's basically just like three nested loops. It's like for all the rows, for all the columns, for all the entries in that pair of row and column. So it's a pretty clear O of n, or a pretty clear n cubed algorithm. And so we can say that multiplying two matrices takes big O. Well, that algorithm takes big theta of n cubed. But we can say generically, multiplying two matrices takes big O of n cubed time. But it turns out that there are more clever algorithms for multiplying matrices that take less than n cubed time. The current record, I believe, is something like n to the 2.37-ish time. And it's actually an open research question whether like it's possible to do better than that. Some people actually think that we'll be able to get, like it's possible to multiply two matrices in essentially n squared time, or maybe n squared plus epsilon for, you know, any small enough epsilon that you want. Some people think no, there's some limit where we're going to hit like, you know, n to the 2 point something is like the lowest you could possibly go. Anyway, it just lets us talk precisely about situations like that where we don't know exactly. All right, let's see. What questions do you have at this point? Okay. So let me write this down. So 3n squared plus 5n minus 7. So that's just an example. Intuitively, how would you classify this using, you know, big O or big theta or whatever?
Theta
Big theta of what?
of n to n squared.
Of n squared. I agree, right? So intuitively, it's like, well, the 3n squared, we don't care about that constant, right? Constant, something multiplying by a constant doesn't matter. And as n gets bigger, right, the n squared term, the 3n squared term kind of dominates, and those other terms become relatively unimportant, right? And so intuitively, yeah, this should be big theta of n squared. If we wanted to actually apply the definition to show that, it sucks. It's super tedious, right? Because it's like, all right, well, we got to actually find, like, even just to show it's big O of n squared, you're like, okay, well, I have to find a constant, maybe I can pick 4 for my constant, because like hopefully it's less than or equal to 4n squared, but it's probably not, like probably for small n it's not, because of the plus 5n is like relatively large when n is small, and so then you have to find like a specific n0 where it's always good. But then you have to prove, like, how do you prove that it's always going to be bigger than that? Like it's super tedious. Nobody wants to do that. Okay, and that's only just proving big O. Then you have to do the same thing for big omega to show that it's big theta. Anyway, but we just kind of intuitively were like, well, intuitively, like the 3n squared is kind of the term that dominates, and we don't care about the constant, so it's n squared. So can we take that intuition and actually make it formal? And it turns out that we can. So in practice, nobody directly applies those definitions. In practice, so let me just say intuitively, big theta of n squared, but applying the definitions is tedious. So the way that we make this formal is by talking about limits. And so calculus is not formally a prerequisite for this class. So I'm not going to assume that everyone has, either seen limits, or maybe you saw them but you forget, or you're like, I never want to see any calculus again. That's fine. So, if this is helpful to you, then great. And but I'm never going to like require you to do stuff with limits or whatever. But it is helpful. And whether or not you remember how to do the formal limit stuff, like maybe just take this as, if it makes sense to you to say, yeah, I can look at that and be like, okay, the 3n squared is kind of the dominant term. As n gets big, that's going to be much bigger than the other things, and so that's the thing that matters. And the constant 3 doesn't matter, so it's n squared. That's great. If you can get that intuition, that's all you really need. But it's nice to see how to actually make that formal. So, theorem. Well, actually, before I say theorem, let me just say the idea is, so we're going to use limits. The key idea is to look at, so if I take, I have some function t of n that I want to analyze, and then I'm comparing it to some g of n, and I want to look at the limit of that as n goes to infinity. Okay? So intuitively, so if, for example, if t of n is growing much more quickly than g of n, so tn gets really big, gets much bigger than g of n, right? Then that fraction is going to get bigger and bigger and bigger. And so the limit, it'll just diverge to infinity. If t of n is growing much more slowly than g of n, so t of n, like as n gets bigger, t of n is much smaller than g of n, right? Then that fraction is going to get smaller and smaller and smaller, and the limit's going to go to 0. And if they're growing at about the same rate, right, then the limit's going to actually exist, and it's going to be like some number like 3 or something, right? And so that's what we can do to classify these. So theorem, if the limit, okay, let me actually say, 0 is less than or equal to the limit as n goes to infinity of tn over gn. And I'm gonna write less than infinity, which, if this were a calculus class, I'd probably get in trouble for writing that, because it's not like it would be not a precise thing to say. What I mean by that is just that the limit actually exists and is equal to some specific number. It doesn't diverge to infinity, right? In a calculus class, you would say if, the limit exists and whatever. But so let me think. Is that the one I didn't want to? Yeah. So, right then, which one is this? I mean, I have to like just think about it hard for a second. So if the limit, it doesn't blow up to infinity, so Tn is not a lot bigger than Gn. So Tn is either about growing at the same rate as G of n, or T of n, if the limit is 0, that means like it's getting smaller and smaller. So T of n is growing much more slowly than Gn. Right? So this would be big O. So Tn is big O of G of n. Right? Tn is growing at a rate that's the same or less than Gn. And so that ratio gets really small. So if, right, conversely, if we say, well, the limit's not 0, and now I would really get in trouble in a calculus class, but less than or equal to infinity just means, well, it either is some number or it diverges to infinity, right? Which one is this?
Big omega.
This is big omega, exactly. So this is saying, look, T of n is growing at the same rate of G of n, or it's growing much more quickly. So the limit goes off to infinity. So this is big omega of G of n. And then, of course, if 0 is less than the limit, which is less than infinity. So in other words, if the limit exists and it's not 0, like it's some specific positive number, right, that's big theta. Okay, so for example, if I look at, 3n squared, what does it say, 3n squared plus 5n minus 7, and I'm like, yeah, I suspect that that's going to be big theta of n squared, but to make that formal, right, if we look at the limit of the ratio of that to n squared, right, well, it's going to be, we can kind of break up this fraction. It's like 3n squared over n squared plus the limit of 5n over n squared plus the limit of negative 7 over n squared. Right here, like the n squareds cancel and we just literally get 3. And here, that's the same as 5 over n. And the limit as n goes to infinity of 5 over n. Right, the n just gets really big, the 5 stays the same, and so it just gets tiny, and it goes to 0. Right, and this is, again, making precise our intuition that the 5n and the minus 7 don't matter as much. They're sort of, as n gets big, they matter less and less. And so they eventually don't really contribute anything. Right, so the limit is 3, and therefore it is big theta of n squared. And again, you don't have to do all this. Like, you can just look at this. If you've done some limits, you can just look at this and be like, oh, I can tell the limit of that over n squared is going to be 3 because, like, again, same reasoning. These other terms don't matter as much, and we're just going to end up with, like, 3n squared over n squared, which is 3. Okay. So, again, you should not have to do this on homeworks or whatever. So on Friday, I'll show you a bunch of examples, and I will use some limits like to prove some theorems about how different rates of growth relate to each other, but then from that point on, you can just like use those facts that I proved, but you don't have to actually use the limits yourself. Okay. Cool. Let's see. As a fun aside, if you like calculus and thinking about this kind of thing, I'll just leave you with a little puzzle that you can think about if you want. This theorem is phrased as an if-then, right? So if this limit has certain properties, right, then it's O or omega or theta, whatever, right? It's not an if and only if. So the converse is not true. In other words, you could say, well, if T of n is big O of G of n, then this limit something, something, something. That's not true. And so I'll let you think about like why that's not true. You have to go back and think hard about what's the definition of big O, big omega, big theta, and why just because something is one of those doesn't actually necessarily imply something about the limit. Anyway, all right, I'll leave it at that for now. Or if you can't figure it out but you're curious, you can come talk to me at office hours and we can talk about it. That's not really relevant for this class, but it is just an interesting aside. Which is why like they aren't defined using limits. That's not the definition. But it is limits are a helpful tool for us. All right. Spend the last little bit talking about properties of, big O, big omega, big theta. Oh, we should talk about. Yeah, talk about that later. There are other things that you'll see, and I'll probably define these for you later. Like there's something called little o, which is basically like when something is big O but not big omega. That's kind of like strictly less than. So if something grows strictly slower than something else. So like n would be little o of n squared. But n squared is not little o of n squared because it's actually... Anyway, I'll define that more carefully later when we need it, but I just realized maybe I should mention it. Okay, so I just want to write down some sort of algebraic properties of these, because a lot of the times when we are analyzing algorithms, like an algorithm is made up of a whole bunch of different pieces, and then we kind of like analyze the pieces separately and come up with like a running time or memory usage or whatever for each of the pieces, then we kind of combine them. And it's useful to think about how kind of, different algebraic things interact with these, because then you can kind of just do it. You don't have to like apply the definition or limits or anything. You can just kind of algebraically manipulate it. So first is if I have some constant times big O of f of n, right? If k is a constant, of course the big O doesn't care about the constant. So the point is, this is just big O of f of n. So I'll say if k is a constant. And I will be careful to say, what do I mean by a constant? So certainly if k is just like a number, that's a constant, right? But it may not always be literally a number. The important point is that it doesn't have n in it, right? So it could be like, square root of a plus b. But as long as a and b don't depend on n, then it is a constant as far as n is concerned, right? So in other words, it won't change as n gets bigger. That makes it a constant. So i.e., doesn't depend on n. Okay, and this corresponds to, running the same algorithm k times. Right? Like, I don't know, we might see an example later where it's like to do this certain thing, you run a breadth first search from here, and then you run another breadth first search from here. So you just do two breadth first searches. So it's just like 2 times whatever, which doesn't matter. So it would be the same as, in terms of big O or big theta or whatever, it would be the same as just running one breadth first search. By the way, these same, I'm going to write big O, but all these properties that I'm listing here, the same properties hold for big omega and big theta. Okay. Okay. What else can we say? If I have big O of f of n plus big O of g of n, well, I mean, you could say it's big O of f of n plus g of n. That is true, but usually there's something more useful you can say. So for example, if I have something that's O n squared and then something else that's O of n and I add them, I could say big O of n squared plus n, but what would be a simpler way to say something equivalent? So if I have n squared plus n, how can I simplify that? Henry? What do you
N
think?
times n plus 1.
N to, oh, well, you're right. I could factor out that, but that's not really simpler. That's just like, I mean, maybe you can think of it as simpler, but that's not simple enough for me. I want even simpler. Yeah, Nico.
Does the second n really matter?
Does that second n really matter?
Considering it already has an n squared.
Yeah, it doesn't, right? Because like we just said that what really matters is the like kind of the biggest term. The n squared dominates the n, and so if we're talking about big O or big omega or whatever, we don't really care about the plus n part, right? This is really just the same as n squared. Okay, so here we can say this is a little imprecise, but we can kind of say like I'm going to say like the max. It's not really max, I guess, because it's like, what does max even mean when you're talking about functions that, but basically it's like whichever term kind of is bigger in the limit. Right? So I'll just say, for example, O of n squared plus O of n equals O of n squared. Right, and this corresponds to running algorithms in sequence. So this is going to come up all the time because every algorithm that we do is going to consist of a sequence of stuff. And if you can break it down and like figure out how long each of those pieces takes, you're like, well, we're going to do these four things. The first thing takes, O of 1, the second thing takes O of n squared, the third thing takes O of n, and the fourth thing takes O of n. So it's like, well, we could say 1 plus n squared plus, 2n, but if we're analyzing it in big O terms, we can just say, well, the whole thing is big O of n squared, because that's the term that dominates. The others don't really matter. Okay, and then the last thing is if we have big O of f of n times big O of g of n. This one is easy. It literally just is O of fn times g of n. And you can't really simplify that. Right, because this would be like if I have O of n times O of n squared, it's like I have something that I'm doing n times, and then for each one of those n things, I'm doing some O of n squared thing. Well, the whole thing is going to take O of n cubed. So this is like, so let me write that down as an example, like O of n squared times O of n is O of n cubed. So this is running like nested algorithms. Right, like imagine you have maybe like two nested loops. Right, and if each loop iterates n times, but they're nested inside of each other, right, that inner one executes n times for each of the iterations of the outside loop, so the whole thing would be n squared. right? Or, you have some loop, but then each time through the loop you call some function or some other algorithm, right? You have to think, okay, how long does that take? And how many loops does this execute, right? So this also comes up a lot when we have things kind of nested inside each other. Questions? There was something else I wanted to say, and I can't remember what it was now. Something about. Yeah.
Is it
Yes.
ever the case that you have more than one variable? Like, if you're doing a loop or something with multiple things?
Very good question. So yes, and we're going to see that pretty soon, actually. So usually when we talk about, we often use n, and maybe it would be helpful if I had been using different variables throughout, because you can get hung up on literally the letter n, and it's like, well, we often use n, but really it's just like the size of whatever the input is or whatever. So we're going to see examples when we start talking about graphs. We're going to talk about a ton of different graph algorithms, and graphs have some number of vertices and some number of edges, and often the algorithms that we come up with end up depending in different ways on the number of vertices and the number of edges. So we will see things where you'll say, oh, this takes time big O of v plus e, or like v squared times e, or something like that, where we actually need to use both to accurately describe how long it takes. It kind of depends on both of them in some non-trivial way. So yeah, it's a great question. Other questions? All right, so on Friday, we're gonna, like on the homework 0, it's like, here's this list of things like O of 1, log n, and so we're just gonna go through like a ton of things like that and look at some examples of each and kind of prove some theorems about how they relate to each other. And that'll be a fun time. So see you then.